All right, good morning, everybody. Hello, hello. Today we've got a fun day. Okay, we're gonna review answers for problem set 1, of which there are some fascinating concepts happening, crossing the boundary, shifting between perimeter and area. Okay, I teased it in a little bit, especially if you did the level 2 questions. You'll have gotten a real feel for, hey, here's this shape, what's the perimeter, what's the area? Here's this shape, slightly different, what's the perimeter, what's the area? You start doing that enough times, you start to find there's a pattern, there's a connection between the two of them that is often overlooked at an elementary level. We're gonna try to examine that a little more closely today, and then you can get started on problem set 2. All right. Okay, but before that, reminder, once again, I need everybody in class after break, or at least as many as possible. So if you haven't already, you need to fill out Odiati's survey, okay? So let him know whether or not you can make it in person after spring break, and if not, what is the reason? What is the actual legitimate reason holding you back? Is it transportation issues? Is it health issues? Is it, family issues? Something happening at home that is not just you personal, how you feel about it, that's not good enough, okay? Got to be a legitimate reason there. Log that with Odiati, and then he'll get back to me, and then I will not be marking you absent if you don't log that reason in. I will be marking you absent if you're not here on your color day, okay? We gotta beat the freshmen, okay? That's the challenge. The freshmen are already here in droves. There's gonna be even more of them after break. The sophomores have to do better than that, right? And plus, we get to build cool stuff in class. So, I think that's all the more reason you need. All right, and Christian has made it, excellent. Okay, so then without further ado, take out your problem set that was due today. And let's review some of these answers and talk about some interesting findings as we go along. So first up, basic perimeter practice. Well, a little bit more than basic, right? I didn't give you the easy ones. Everybody can do regular rectangles. We're like, okay, if you really understand how perimeter works, then you could figure these out. Understanding the diagram, noting, oh, this mark means this is also 3.1 inches. Okay, add all 6 sides up there. And this funny looking thing here, right, get the perimeter there. Make sure you include the correct units. This double apostrophe here means inches. So you could have also written this as 33.05 inches. But when in doubt, just copy the same symbol that you see there in the figure, right? Okay, next up, good old tetrominoes. Make a comeback. You cannot escape these shapes. They're just everywhere. What about the perimeters of the tetrominoes? Well, turns out since there were only 5 possible unique configurations, okay, flipping them over won't change this. 4 of them have all the same maximum perimeter of 10, and there's only 1 that has the minimum of 8. There's no in between. All right, how about toothpick shapes? All right, so our lines of toothpick shapes increase in perimeter with the following patterns here. And I think even from these three, you can kind of see that this is a pattern of perimeter of triangles. This is the pattern for perimeter of a series of squares, and so on. And looking vertically, now there's a pattern in the patterns. There's always plus 2. There's always, I started with n, and then 2n, and then 3n. I'm just counting up n's, right? And then 4n, and then no, wait, we skipped to 6n. Well, what was different? Well, we skipped from hexagon to octagon. We didn't stop at septagon, right? So it's not just counting up, but it is related specifically to the number of sides. So for some m-sided polygon, the toothpicks in a row of n of those would be m minus 2, so sides minus 2. Notice my octagon, 8 sides, has 6. So that number times n, number of figures, plus 2. And now we had, this is a real interesting one, square and a circle, both made out of wire with the same area. I don't know how they managed it. Very careful measuring, and that's the setup, right? We already know they have the same area. So if I were to flatten them out, okay, nice and straight wire, and just measure it with a ruler, how long is each one? I.e., what is the perimeter of a square with a given area and the circumference of a circle with a given area? And if they have the same given area, how do those perimeters compare? Turns out the square is longer by 1.95 centimeters. Okay, how about scaling? I think I originally meant to include a similar, I think like number 19 is like the same question, but it asks about the perimeter. I just skipped straight to area. What happens to the area of a rectangle if you multiply both its length and width by 2? If I multiply the length by 2, twice as long of a rectangle, its area doubles. If I multiply the width by 2, twice as wide of a rectangle, its area doubles. If you do both of that, you multiplied by 2 and multiplied by 2 again. You have effectively multiplied by 4. The area is 4 times the original. Both sides by 3, 9 times the area, by 10, 100 times the area. For however n bigger you make each side, you make it n squared times bigger. All right, and back to just some straight up perimeter and area practice on triangles here. Nothing too fancy. We just went ahead and rounded this one on C to 2 decimal places. If you have something close to that, or that rounds to that, or this could round to your answer. If you put 17.1, that's fine. It didn't specify 2 decimals. Okay, any questions on the level 1 problems? No? Okay. Let's keep going. So here then are the level 2 natural extension. We did the tetrominoes. Here's the pentominoes. Remember, 5 squares all connected together. So the maximum perimeter you can achieve is 12. This is one example. There's a lot of them, right? The basic L shape. Okay. And the minimum perimeter you can get is 10 with only this guy nice and packed tightly in there. Okay. So if you compare that then to how the tetrominoes were, following the pentominoes, what are the numbers here? What's the pattern going? Extend that out to, say, 8 squares at a time. You would get a maximum of 18 perimeter, something long and skinny like this, or again, it could have a bend in it at any point, and that's fine. And the minimum is 12 if you pack them all into this rectangle. Okay, similar concept. Toothpicks in a square. Count the number of toothpicks, you have the perimeter. Multiply to get the area. There's our starting point. Not very interesting. But what is interesting is when we compare it to this. Right? This scenario, I've rearranged the toothpicks, still have my large square for the most part, but I've moved these toothpicks from the corners and I've like dented in the corners, right? Like pushed it in, boom, boom, right? And so now it takes the same number of toothpicks to go around the figure. I still have a perimeter of 28, right? I just moved these inside. But now this square, as it were, is no longer inside. If this was my fenced-in area, okay? You're building your sheep pen for Minecraft, okay? Number of squares inside the pen. Look what happens to the area. If you nick out those corners, you go from 49 to 45. Okay? And you could find that really easy by subtracting. Well, I literally took out one square from each corner. That's 4 squares. 49 minus 4 leaves 45. We'll do it again. Take out a bigger square out of each corner. Okay, well, now I'm missing a 2 by 2 square from each corner. Right, so 2 times 2 is 4 times 4. Subtract that from 49. That area's down to 33. Still using the same 28 toothpicks. So what if we go again? 3 toothpicks per side of corners reduced. 28 perimeter, 13 square units of area. Gosh, it's tiny. So what is the pattern going on here? Something to this effect, right? The perimeter stays constant. It is always 4 times the side length, right? In this case, it's a 7 by 7, 4 times 7, right? You can make it any square size you want. The area decreases as the corner squares increase. Makes it, you're taking away a larger chunk, so you're going to decrease the area. Specifically, however long you make your square, the big square is m squared, minus 4 corners, each of n squared, the small size that you're taking out. All right, next up. This is hitting right at the heart of it. If you haven't got the idea yet, I hope this question makes it clear to you. 2 rectangles have the same perimeter of 40 meters. Do they also have the same area? Try several examples to test your conjecture. The answer has to be no. We kind of already got a feel for that in the squares from before, right? We can make a shape with the same perimeter. Or here's basic ones right here. A 15 by 5 rectangle. Perimeter is total of 40, 75 area. Make that a 10 by 10 square, still 40 perimeter. Now I have 100 area. How much better this is, right? Okay, how about perimeter and area of these triangles? A little more practice there. And I think that was, oh, there's the last triangle. Okay, any questions on the level 2 problems? Okay, finally, I will go over the level 3 here. This one was just some fascinating little bits of geometry here. So check out this guy. We've got a rectangle here and a large triangle there, or you can think about it as a rectangle with an extra triangle on top. But this is all, one length here. And it says specifically side ED, so that's this guy here, is twice the length of CD. Ah, so it's not just any line out there. Specifically made it so that this segment is congruent to that segment. So then how does the area of the rectangle and triangle AED compare? Turns out they are exactly equal to each other, okay? Because if this side is twice that side, but they have the same base here, I'm multiplying whatever the numbers are, okay? Work with me a little bit here. Abstractly, I multiplied this base times this side to get the area of the rectangle, yes? For the triangle, I multiplied this same base, AD, times now this double length of the side. So if this was a whole rectangle, it'd be twice as big, but it's a triangle, so it's only half. Right? So I multiply by 2 and multiply by 1/2 because triangle, so now I'm back to where I started, the same thing. That's kind of neat. Another way you can look at it is you can see that this triangle formed here will fit perfectly inside of this triangle formed there. All right. And then finally, the most brain-bending puzzler. 2 coins shown have a radii of 3 centimeters and 1 centimeter. So this is 3 times the width of this guy. Smaller coin rolls around the circumference of the larger coin. Okay? Not just spin freely, but roll it, keep them strictly in contact so one does not leave the other. I think I've got a pair of circular objects here. It's out here, right? So we've got a bunch of junk in this bowl. I gotta clean that out. Okay, I've got the bat bowl here. You stand. So you've got a circle on top of a circle, and you want to roll it along, right? So it moves smoothly, as if it was a tire on the road, right? So the question then becomes, how many times does the small one rotate? When does it, whatever was the top, when is the top, facing upward again? How many times does that happen? It's own little revolutions by the time it goes all the way around the big circle. And you would think it's got 1/3 of the radius, right? The big circle is 3 times as wide. The circumference, also a linear distance, is 3 times as long, right? That's what we're comparing here. We're wrapping this circumference around that circumference. You would think it should be 3. And if it was just the distances of the circumference to compare to, it would be 3. But paradoxically, it turns out it's actually 4. This is fascinating. There's a whole Wikipedia article about this. It's called the coin rotation paradox. Okay? Coin rotation paradox is the counterintuitive observation that when one coin is rolled around the rim of another coin of equal size, the moving coin completes 2 full rotations after going all the way around the stationary coin. Take a look at Mr. Washington here. Okay? So we want to roll it nice and even, no slipping. Okay? Quarters are great for this because they got those little grooves on the edge. And watch how just going halfway around the tail side coin, Washington's head has made a full loop. He's back right side up. So naturally, if we were to continue that and have him go around the bottom half of the tails coin, he'll complete another loop, and he'll have spun himself around twice, going around one loop of the other coin, which doesn't make any sense. Their circumferences are equal. They should match up 1 to 1, right? You would think that. That's the paradoxical part. It seems counterintuitive. Okay? But the problem is that one of them is moving and one of them is stationary. That's the issue. If you had 2 rotating together, like gears meshing, yeah, they would rotate 1 to 1. But one of them stays put. And so not only is the quarter that's moving, turning itself, but it's also moving in another circle. That's the thing that you're missing. It's moving in two circles, its own rotation and its revolution around, just like the moon. And that's what they get out here, this comparison, right? Okay. Now, for our problem, we can come down here. What about unequal radii? What if they're not exactly the same? So it's not just double. Take a look at this picture. Diagram number 1, up at the top. I have my rainbow bordered coin, so you can like track its edges as it goes around. The arrow points up. As it rolls along this flat surface, we are counting number of times the arrow turns back to pointing up, right? 1, 2, 3. And work out for yourself how the colors match up. I've got light gray there on the bottom of the coin, and then it goes to dark gray, and then to purple. And so as it rolls, that purple side of the coin will be on the purple part of the flat line there. Match up perfectly, right? So I have the distance rolled is 3 times my circumference. So I have rotated 3 times. That's exactly what we expected to happen. But look what happens when you take that exact same scenario. Pick up that flat line path that the coin rolled on, that bit of road, as it were, that the tire ran over, and bend that around into a circle. Now in diagram 2, what happens? I still match up light gray to light gray, then dark gray lands on dark gray, then purple lands on purple, and my arrow is pointing sideways. It's pointing to the right relative to the large circle. Relative to that surface, it's pointing to the right. But to us, looking at it now, right, not relative to the surface, but it's pointing diagonally. Right? It's not pointing perfectly horizontally now. And then I reach 1 rotation down here. Now it's finally pointing back up. And then there's 2 rotations, 3 rotations, 4 rotations, all the way around. Because bending the path that it rolled along, bending its road, as it were, into another circle, added an extra circle. It added an extra revolution. It was spinning in place 3 times, and then you took all of those spins and rotated them around once. 4 times. Right? If we're talking about an absolute rotation, okay? From our viewpoint, right, outside of the large circle, we see how often does the arrow point up? That's 4 times. If instead you want to see how many times does the coin touch the large circle at the same points, that would be when does black and gray meet black and gray. That you can see is 3 times. So once there at the top, once down here at 4 o'clock, and then once again there at 8 o'clock, right? Black and gray, black and gray. And notice at those 2 points down below on either side, the arrow is pointing up relative to the surface of the large circle, right? If that was the surface of the Earth, that would be up, looking outside, right? It's like Australians, okay? They're not hanging upside down. Relative to the surface of the Earth, everything is pointing up, right? But if you go to the moon and you look back, okay, there's the Earth way out there, and things are pointing up, and this points right outward from the center of the circle. That makes the difference. Miss Need, your brain hurt yet? Okay. Any questions on those problems? Last call. Okay, then I have one final bonus question for you. What kinds of shapes have the highest perimeter to area ratio? And second, what kinds of shapes have the lowest perimeter to area ratio? Just think about all those problems we've been doing where we tracked perimeter and area of things as they changed, compared situations to each other. If I was to take the perimeter and the area and say divide those numbers, right? Go back to say the toothpick square. Okay? You divide one by the other. What gives you the highest result? What gives you the lowest result? What types of shapes? How would you describe those shapes that give the most extreme answers? And in fact, I should have thought of this earlier. I do want you to actually write this down. So let me pose this as a question here on Google Classroom real quick, and then you can type up your answer. Some spaces in there. There we go. Okay. All right, there you go. So refresh your classroom page, and there should be a new post asking about the perimeter to area ratio. So think about that. How do you describe, in general, what types of shapes? So you can be very specific with your definition. Oh, it's always squares, or it's always triangles. Every type of triangle? Every type? Well, there's only one type of square, right? What about other polygons? Circles even, right? Think back to the tetrominoes and pentominoes. How would you describe the long? They all have the same area, right? Same number of squares. They have different perimeters. So some have a higher, some have a lower ratio. How would you describe those guys? So take a few minutes here, type up your answer to that, and then we'll, let's see, give you 2 more minutes on that, then we'll discuss it for a bit, and I'll leave you the rest of the time to start problem set 2. Okay, so let's talk about this a little bit. Let's try to narrow things down. What if we think of only rectangles? Rectangles only. If you want the highest perimeter to area, most perimeter, least amount of area, how would you describe those rectangles? What words would you use? Think about the pentominoes, right? The ones that had the most perimeter would be these guys, right? How would you describe that? Long and skinny. Exactly. Yeah, those are the exact same words that came to my mind. Long, skinny rectangles. Right? Barely any space in there. But you got to run fencing all the way down and all the way back, right? Okay, how about the lowest perimeter to area ratio? So the most area using the least amount of perimeter possible. You would want to do the opposite, right? Instead of long and skinny, you'd make it, I guess if we were using the actual opposite words, you'd call it like short and fat, right? In fact, the best rectangle for the job would be what? Square. Right? How about, let's go one step further. Let's go consider all regular polygons. Using a square as our baseline. Is there a polygon that would have a higher perimeter to area ratio? Can we do worse than square? The circle has more perimeter and less area? Well, first of all, circle's not a polygon. You've gone too far. We'll save circles for the end. Think about just the next stage. This is 4 sides, so 3 sides. I hope that would have turned out more equilateral, but and 1, 2, 3, 4, 5. Nope, didn't work. 1, 2, 3, 4, 5. Come on. I know it's done it before. I just have to make it bigger. No? There we go. Okay, scale that down. Oh my God, pentagon. How do they compare? What do you think? Here, didn't we? What do we have for comparison? Look at this guy. That got composed of longer and skinnier rectangles, which use the same descriptions. Which ones seem more long and skinny versus short and fat? Which ones are more extreme? Think about this. Compare to the center point, right? We're going to do this geometrically. We're going to do it properly. Geometry is about measurement. Think about measurements. So from the center, this has a very short distance and a very long distance, right? The square from the center has the same distance in all, at least straight to the sides, right? What about the corners? Long, skinny triangle, we can also go out to the corner. That's also a long distance compared to a very short distance. Square has a distance out to its corner, but it's not nearly as extreme, right? We can compare any diagonal length to the side length, and they're much closer to each other than these two, right? We could use that as a measure of the extremeness, how long, skinny the rectangle is. And we could also use that inside these shapes. We could go to the side and to the corner, and we can go to the side and we can go to the corner, and we can go to a side and to a corner. Which one has the greatest difference between those distances? Which one has the longest, pointiest bits? It's the triangle, right? Isn't the triangle the closest analogy of the regular polygons to our long, skinny rectangle? It has the most extreme of options. Whereas with the polygon, right, the more sides, the better if you want to minimize perimeter to area ratio. Because each side is not that long, right? The more sides you put on it, to keep the same given relative size of the shape, each side itself has to get smaller and smaller. Which means that gap between going to the middle of the side versus the corner, they get closer and closer together. Until the most extreme, the absolute best two-dimensional figure with the absolute lowest perimeter to area ratio is? You guys said it. The circle. We can think of the circle as having almost infinite sides, right? Infinite sides of infinitesimally non-existent length, right? Because it's infinite points around. Isn't that neat? This is why, if you're going to fence in a region, say for your, you're building a pen for your sheep in Minecraft, the closer you can get to a circle, the better your perimeter to area ratio is. You will use the fewest number of fences for the same area. All right. All right, any questions about that? Okay. I've got 3 answers there on Google Classroom. If you guys haven't already, use my information here. Write up your own answer there in your own words to the classroom post, and then turn to problem set 2, which has some really awesome things. I'll highlight a couple of them here. Huron's formula, super cool, crazy shortcut for finding the area of things you otherwise couldn't find the area of. Okay, so this is like a neat math competition kind of trick. They like to trip people up and say, oh, you can't find the area with it. If you know Huron's formula, you can do some insane stuff. I think we've talked about Sierpinski's triangle before, the triforce within a triforce within a triforce looking thing. Here's Sierpinski's carpet, which is the same thing with squares. There's a little question about that. It's kind of fun. And we got some good old floor plan, area, carpeting practice. Pick's theorem, this is the new one. Other strange ways of approximating area when you can't otherwise calculate it. And then the level 3 are some neat applications there. All right? Okay, so with the question on classroom and problem set, I will leave you to start with that.